Okay, so a couple of weeks ago we introduced the theory of probability and stochastic processes, and I mentioned to you that I am introducing these concepts because I would like to deal with an additional method for synthetic river flow generation. We discussed about the use of rate form of modeling first, and then I mentioned another opportunity, which is stochastic modeling. And I also mentioned the fact that in order to introduce stochastic modeling, I need to introduce also some concepts of probability and statistics. So now let me try to go back to these issues, and in particular to go back to the definition of probability. Okay, and I already mentioned that accordingly to one definition, probability of a given event can be defined as the frequency with which this event occurs on a large sample. So one way of estimating the probability of a given event, I said, is to count how many times this event occurs during some experiments. Now, this is quite simple if we talk about discrete events, meaning that it's relatively easy to count the probability of the random variable capital X to take a specific value lowercase x, which is equal to, let's say, the number, and let me indicate the number of times that this event occurs with the symbol capital N, as the number in which we observe that capital X is equal to lowercase x divided by the total number of experiments. This is what I said. And also, I said that usually, in order to get more flexibility to deal with the event, we introduce the random variables. Random variables are associations between events and the real numbers. Okay, then, if the random variables, this is what I already said, are discrete variables, like an event that can take just two values, 0, 1, and this could be, for instance, the experiment of tossing a coin. If we indicate with 0 the head and 1 the cross, we have a random variable, which is the result of an event that can take just two values, 0 or 1. So it's very easy in this way to compute probability accordingly to this definition by just repeating the experiment and counting how many times I find the 0 outcome against the times that I find the 1 outcome. So in this case, the random variable is discrete, and if it is discrete, this is quite easy to understand. I am insisting on these concepts because I would like that you understand the physical meaning behind the definition of probability. So this kind of treatment of probability theory is something that I am trying to provide to you in a very applied fashion. So again, if we concentrate on a discrete random variable, and discrete random variable for us, for instance, in hydrology, could be whether or not a day is rainy. So we could say, to perform this experiment, every day I assign to that day a 0 if it did not rain, and a 1 if it rained. And therefore, this is a typical discrete random variable. Did it rain that day or not? 0 if not, 1 if yes. And it's very easy if you have say 10 years of observations to count how many times you got 0, no rain, and how many times you got 1, rain. So in this case, when the random variable is discrete again, it's easy to understand the physical meaning of probability, accordingly to the definition which says that probability can be approximated with the frequency of an event. The problem gets more complicated when the random variable is continuous. It's not more complicated, it's more complicated to understand the physical meaning. Because if you have now an ax between, let's say that the random variable is defined between 0 and 1, and can take any real value between 0 and 1. In this case, it's difficult to understand this definition, because given that you have infinite real numbers between 0 and 1, if you count the number of times that each one of them occurs, this number is 0. Because given that you have infinite numbers of digits, and if you observe, for instance, rainfall, you never get a precise value. If you fix an x between 0 and 1 as a lowercase x with an infinite number of digits, and you compare this x with rainfall, you will never find a match. So according to this definition, you would say probability of getting this precise value of x is 0. So there is the need to adapt this definition for the case of continuous random variable. And I said that in order to gain a better understanding of what probability means in this case, it is more appropriate to introduce the probability that capital X is greater or equal to lowercase x. In this case, to assign the physical meaning is easier. And you can still use this definition of probability, this way to compute probability. Of course, here you have to put a minus sign here. And in this case, if you fix a lowercase x, which is a given value, for instance, for rainfall or river flow, then if you have a long record, it's easy to compute the number of times that you got a river flow lower or equal to x. So it's easy also to compute probability and, above all, to understand what probability means. So I said, let's, for the case of continuous variable, to refer to this probability of not exceedance, not probability of getting a precise value. But still, let me move one step back and now try to understand how I can define the probability of getting a fixed value. So let me move one step back again. We will get back again to this definition of probability of not exceedance, but let me concentrate once again on this problem. Let's say that I want to understand what's going on here. I want to understand what is the probability of getting a precise value of a continuous variable, and within this perspective, let's see how we can elaborate the definition, and especially how we can understand the definition. So, now, let me define the probability of getting a precise value of a continuous variable, lowercase x, in this way, as, let me define an interval around x, which is a width that is 2 times delta x, and this delta x is infinitesimally small. So let me define this interval around x, and let me compute the probability of getting this result. Uppercase capital X is, lowercase x is minor or equal than capital X, minor or equal than x minus delta x, x plus delta x. So let me define probability in this way. Let me take the value lowercase x minus delta x, and let me count the number of times that capital X is comprised between lowercase x minus delta x and lowercase x plus delta x. So what I'm counting now? I'm counting the number of times that my random variable falls within an infinitesimally small range around lowercase x. Okay, and now let me divide this probability for the width of this range. Why I'm dividing the probability for the width of the range? Because, of course, here I'm counting the number of times that infinite number of the random variable can occur, because within this small interval I have infinite values of this continuous variable, and therefore I'm counting the times that more than one event occur, and therefore to refer to each single one I have to divide for the width of the range. And now it's easy to understand the physical, let's say it's easier to understand the physical meaning. In this case, I count the number of times that I get my variable falling within a range, which is finite, is not zero. But because I refer to a range, then I divide this number of occurrences for the range width. And this is also reasonable because if you think about increasing the range, you get more values falling into the range, so it's quite obvious that you have to divide for a greater number to estimate the probability. And what happens instead, if you decrease the value of delta x, what happens is that the numerator tends to 0, because of course if you decrease this interval and you allow it to get infinitesimally small, then this number of times that the random variable falls within the range tends to 0, but it tends to 0 also the denominator. So, if you compute the limit for delta x tending to 0 of this quantity here, you converge to what? To a finite number, which is the probability of capital X equal to x, to lowercase x. This is the way in which we can define the probability for a continuous variable, which is not a probability of not exceedance. This is probability. Usually this probability of getting x equal to an assigned value lowercase x is indicated in statistics with the symbol lowercase f of lowercase x. This is just a symbology. In order to simplify the notation, usually in statistics they use, which stands for frequency f. Use the symbol lowercase f. Okay, now let's think about the random variable defined on this range between 0 and 1. And let's go back to the probability of not exceedance. What is the relation between the probability of not exceedance and this probability that we have defined in this way? It's easy to understand that the relationship is an integration. So I can write that the probability of, I use the same symbology, capital X lower or equal than lowercase x is given by the integral between, in this case, 0, because the random variable is defined. It was my assumption between 0 and 1, so I have to start from 0. 0 and lowercase x of fx dx. And let's try to understand if this is indeed true. What happens if I compute this integral between 0 and x? So let's say that we start from here and we compute this integral in this direction until here. Until here. So the integral, again, is the integral of what? The probability, as it was defined here, times the x. So we take the probability, we multiply it times the x and take the summation. This is basically what the integral does. So if you take a delta x, start from 0, take a delta x, multiply it for dx, you obtain the number of times that you get an event occurring in the first dx. And then you sum all the number of times, and indeed you understand that you get a probability of getting outcomes that are lower or equal than x. Again, you go forward delta x by delta x, you take the probability defined in this way, which is number of times that the random variable falls within each delta x, and you multiply times dx, which is what we divided here. So at the end of the integral, you indeed get the number of times that your random variable fell inside the range 0x. And this is a very important relationship. The probability of not exceedance is given by the integral of the probability. And usually in statistics this is indicated with the symbol capital F of lowercase x. To be clear, I should better distinguish capital X between lowercase x. Let me try to do this. Okay, then this is a relationship that you have to well remember, and that you can also write in this way. You can say that the probability is the derivative of the probability of not exceedance. So you can say that lowercase f is equal to the derivative of uppercase x over dx. So the probability of not exceedance is the integral of the probability, which is, in a way, quite easy to understand if you think to probability of not exceeding a river flow of 100 cubic meters per second, which is the integral of getting any single value that is lower or equal to 100 cubic meters per second. Okay. me see. Okay, now, we already said that it's very useful to describe the probabilities by using analytical relationships, which are called probability distributions. And sorry, there is one thing that I wanted to say, which I forgot. I was thinking about what I had to say. I called lowercase f probability, and this one probability of not exceedance. In statistics, very often they use a different couple of terms, which is probability density for lowercase f, densità di probabilità in Italian, and cumulative probability for uppercase f, probabilità cumulata. In Italian is densità di probabilità and probabilità cumulata for respectively lowercase f and capital F. In English is probability density and cumulative probability or cumulative density. So sometimes they use the symbols. I have to insist on symbols because they are very much used, very often used. They use the symbol PDF. PDF. I'm thinking about the symbol, that the acronym that is more used. It is for sure CDF for the capital F, which is cumulative density function. And it's PDF for the density, which is probability density function, yes. So very often you find the symbols PDF and CDF. Okay, as I said, it's very useful to have analytical relationship that give to you the value of the PDF and CDF, the value of probability and probability of not exceedance. And there are some very much used formulations, and I think I already introduced a very significant one, which is a Gaussian distribution. A Gaussian distribution can be written explicitly. We can write explicitly only the PDF. So the PDF of the Gaussian distribution, because the CDF involves an integral. And the PDF is fx is equal to 1 over square root of 2 pi sigma square e to the power of minus x men mi x square. Now, afterwards I have to check because I don't remember well. I think this is the formulation. Let me check. You don't have to learn it by memory. Yes, it is correct. You don't have to learn it by memory, but this is the formulation. And let me see if I can connect to this projector. It's my problem here, the problem with the PC, and let me try to configure it. And dimension. Let's see what happens. Just because I wanted to show you some graphs about the Gaussian distribution and almost. It's very strange that it's let me see if I can. Let me see if it improves. Seems not. Just 1 second, I make a last attempt. Otherwise, I try to reproduce the graph. Okay, let's try. I'm not very confident, but understand why. Okay, in any case, this probability distribution, it is shaped in this way. If you, of course, let me make a premise. You see two parameters here, which are mi and sigma and sigma. Mi is the mean value of the random variable, and sigma is the standard deviation, which quantifies the variability of the random variable. So let's suppose that the mean is 0 and the standard deviation is generic. Then the shape of the probability distribution, the PDF, small f, is like a bell, and it's symmetric. So you get the same probabilities for values that are lower than the mean and greater than the mean. And I already mentioned to you that this distribution has the nice property that if you aggregate any hydrological variable, you get a distribution that is Gaussian, and it has also the nice probability, the nice feature to be indeed symmetric. If you compute the integral of this curve, first of all, please note that accordingly to the definition of the probability, the integral of the curve is 1, because probability is varying between 0 and 1, so the probability of not exceedance should cumulate to 1. And if you compute the integral of this bell-shaped curve, you get a shape like this. So if this is 0, you get something like this, where this is 1. Okay. Now let me introduce one more distribution. There are plenty of distributions that I could introduce, but I don't want to spend much time on this. Let me introduce one more distribution which is very important, and we will see why. And the second distribution I would like to introduce is the uniform distribution. The uniform distribution is defined over a range. Let's call it the extremes of the range, let's call them A and B. And the uniform distribution, therefore, it's indicated usually with the symbol U, that is followed by the two parameters, A and B. And the uniform distribution is equal to 1 divided by B minus A for A greater or equal than X greater or equal than B, and it's 0 for X lower than A and X greater than B. The uniform distribution, as its name says, assigns equal probability to any value that is included in the range of the distribution. And if you look at the graphs of the PDF and CDF, they look very simply in this way. If you put the lowercase f here, and here on the x-axis you have the values, the PDF is like so, which is 1 over B minus A, this is the PDF, which is uniform, and the integral is capital F between A and B is equal to this. This is 1. It's equal to, I use the blue, is equal to this is 0, and then a straight line, and then here. This is the uniform distribution. Usually the uniform distribution is defined between 0 and 1, but just for an agreement, just for convention. Conventionally defined on 0, 1. These are two distributions, the Gaussian and the uniform, that are not very useful to model hydrological variables because, as I said, hydrological variables usually do not follow either one, neither the Gaussian nor the uniform. So usually we have to adopt other distributions, and one distribution that is useful in hydrology is the log normal, that is simply the logarithm of the Gaussian distribution. It means that if your hydrological variable is not Gaussian, you take the logarithm of the variable, like the logarithm of the river flow, and then you will find that the result, the logarithm, is close to Gaussian. This occurs often. There are many hydrological variables that are log normal. Also, the log normal distribution is positively defined because the logarithm can be computed only for positive values, and therefore this is a feature that makes the distribution more appropriate for hydrological variables that usually are positive. Not always, but if you think about rainfall and river flows, they are positive variables. So it's better to use a probability distribution that is positively defined. So the log normal is a good option, otherwise there are many other distributions. Once that you knew the probability distribution of a random variable, it's very easy to generate synthetic outcomes from the random variable. Outcome is the word, the English term that is used to define events that are sampled, taken from a probability distribution. When you talk about probability distribution, you talk about probability of outcomes. The probability distribution models the events, but if you extract an event from the probability distribution, we use the word outcome from the distribution. again, if you knew the probability distribution of a random variable, it's very easy to generate synthetic variables. And I would like to explain how we can do, because this is important, and I wanted also to show, but I will do it tomorrow. I wanted to show it on the PC, but we'll do tomorrow. So how can I generate an outcome from a given probability distribution like the Gaussian? First of all, I have to know the parameters of the distribution. If I talk about the Gaussian distribution, I need to know the mean, and the standard deviation, sigma. So first of all, I have to estimate these parameters. And to estimate the parameters, of course, I have to use events. So I have to perform experiments and compute the parameters. Like we did for Reinforth models, we have to calibrate the probability distribution. And I'm not now